Welcome back, fellow math explorers. Today we are stepping onto the mathematical field for a trailing match against separable spaces. So, as a motivation, picture a bustling city, right, with countless streets and intersections. In this mathematical metropolis, separable spaces would be like well-placed benches, for instance, right, scattered throughout the city. So these benches, of course, are not just ordinary. I mean, they are strategically positioned so that no matter where you are always just a short walk away from one. So, I mean, this means that no matter how vast and complex our mathematical city becomes, there is always I would say, a nearby resting spot, right? So, in mathematical terms, we will say, I mean, there's kind of a countable dense subset that we can rely on. So it's like having a friend, right, that you can easily meet no matter where you are in the city. So in the realm of mathematics, separable spaces play a very crucial role, right? So they are like, as I said earlier, I mean, they are like meeting points for concepts and ideas, making it easier to explore or understand various mathematical avenues, as we will see, for instance, in this lecture, how, I mean, the um, how separable spaces intertwine with reflexivity and weak topology and weak star topology, for instance. So I strongly invite you actually to, I mean, to take a stroll right through our mathematical city, where separable spaces act as the friendly landmarks that keep us oriented and connected. So we start with a definition. So definition. So we say that the metric space E, so we say that the metric space E is separable if there exists, I mean, a set D. So if I put it in color, if there exists, I mean, if E contains a countable dense subset, so if there exists a subset D, right, of E such that that is countable and dense. Okay, so let's have some, I mean, very short remark. So finite dimensional spaces are always separable. So finite dimensional spaces are separable. Like this is due to the fact that I mean if you have a finite dimensional space, then it is isomorphic to say Rn, right? If the dimension of your space is n, and then you know that Q is dense in R, so there's basically nothing to prove here. So also we will see in the probably next lecture that LP spaces are also separable, right? For P, so maybe I write it down for you. LP and small LP, right? Are separable, right? This for every P between 1 and plus infinity. Also, the space of continuous function on the compact metric space is separable. This is the space of space of continuous function, a compact metric space. Is separable. I think this is actually this is due to the Azela-Scully theorem, right? So, but maybe we'll come to that, so don't worry. Okay, good. So let's state our first proposition. So proposition 3.25, in continuation, of course, with the previous video. Proposition 3.25. So let E be a separable. So let E be a separable space. Right, and let F, right, be any subset of E. Then F is separable. So any subset of a separable space is actually separable. Then F is separable. So let me just write that separability here. It's important. Okay, good. So let's have a look at the proof. So of course, assume E is separable. So assume E is separable metric space. Right, and let so this means there exists a countable dense subset G. So this means there exists countable dense subset that we call Z, right, of E. So of course we can always assume that say Z mirrors the following form. Those are the UN, right, such that and just the sequence UN. Okay, so now let say Rm, right, be any sequence of strictly positive numbers. So any sequence of strictly positive numbers, right, such that Rm actually goes to 0, right, as m goes to plus infinity, of course. Now consider the set, the following set. So put delta, right, define delta to be the set of point nm, right, such that the ball, the open ball, of course, around un and radius rm intersected with f is non-empty. So let me drag it. Okay, good, such that this is non-empty. Good. So delta, of course, is delta is non-empty, right? Otherwise it's non-empty, otherwise G is not dense. In E. So then for each say nm, right, belonging to delta, one can actually choose I mean there is say we call it an ANM, right, belonging to the intersection UNRM intersected with F, right? And then now the only thing you have to do is now to define, I mean, say G tilde to be the set of those points. Let's put MN. Okay, such that NM belong to the set of natural numbers. So then, by definition of, I mean, the intercept that G tilde is actually countable, right? So then G tilde is countable. It's countable and dense, I mean, is, let me put this, a countable and dense subset of F. And then subset of F. So I mean, it is obvious that GTH is countable. So I mean, denseness comes from, I mean, we just write it. So denseness actually, I mean, comes immediately from the definition of the point AMN. So and then you can conclude that F is separable. And then we are done. Okay, good. So now we can state a very important theorem. So theorem 3.26. So let E be a Banach space such that, so let E be a Banach space such that the dual space is actually separable, such that, we put it in color, such that the dual space is separable. Then E is separable. Okay, so if you have a Banach space for which the dual space is actually separable, then the space E itself is actually separable. So before going to the proof, so let's have a remark. Okay, so first thing to notice that, let me put it in color, the converse is not true. The converse is not true. I mean, if a space is separable, it doesn't mean that the dual space is necessarily separable. So the converse is not true, right? Maybe we see that, for instance, when we discuss the LP spaces, maybe we see, for instance, that the set E, which is say equals to L1, is separable, right? But the dual of L1 is not separable. So this is separable, right? But its dual E star, which is actually L infinity, is not separable. So this is, this would be a kind of a counterexample. Okay, good. So let's go into the proof. For the proof, we obviously assuming that the dual space is separable, and then our goal is actually to show that A is separable. So let Fn, right, be n greater or equal than 1 be a countable dense say be countable and dense in, so we don't need the A, be countable and dense in the dual space E star. Right, this is, I mean, this comes from the separability of the dual space. Okay, since for every n, right, you have by definition of the operator norm that the norm of Fn is the supremum, right, of the absolute value of Fn of x, right, or the x in E such that x is less or equal than 1, right? So we can find some xn in E, right, such that, put it here, the norm of xn equals 1, and Fn of x is actually greater or equal than 1 over 2 norm of Fn. Right, I mean, this comes from the definition, the characterization of the supremum. This is what I mean. If you have A which is equal to, say, the supremum of a set capital A, so this means that x is less or equal than A for every x in A, and for every epsilon positive, right? So I can always find an element in the set A, right, that obviously depends on epsilon, such that whenever I remove something from the supremum, it is no more the supremum, so that such that A minus epsilon is actually slightly less than B of epsilon. So you can easily make the analogy by say by taking epsilon to be 1 over 2 norm of Fn, right, and then our B of epsilon would be Fn of xn. Okay, good. So this would be the analogy, right, to find this. Okay, now let's denote by, say L0, right, the vector space over the rational numbers, right, generated by the xn. So this means that L0, I mean, we know how to define the span, right? So this means that L0 consists of all finite linear combinations with coefficient in Q, right, of elements xn n greater or equal than 1. So now we claim that L0 is actually countable. So claim L0 is is countable. So for the proof, so indeed, for every n in n, right? So let's say, oops, let's say lambda n might be the vector space over Q generated by the xk, right? K running from 1 to n. So I mean, so gamma n is lambda n is just in the span of x1 up to xn, right? But over Q actually. So the coefficients are actually in Q. So clearly, I mean, lambda n is countable, right? Clearly lambda n is countable, and over you can write L0 as being the union of the lambda n, right, and running from 1 to infinity. So it is clear that, I mean, L0 is actually countable union of countable sets. Okay, now so L0 is countable. Now let L, right, denote the vector space over R generated by the Xn. So denote the vector space over R now, right, generated by the Xn. Of course, I mean, because Q is dense in R, so you have to still have that L0 is dense in L, right? Because L0, I mean, it's just, I mean, it's also the vector space, but over Q generated by the Xn. So obviously L0 is actually dense in L. So our second claim is that L is actually dense in E. So L is dense in E, right? And this we conclude the proof, right? So let me just put it in brackets. So on this, we conclude the proof. Conclude the proof as L0 is, I mean, let's say L0 will be countable dense subset of E. Okay, good. So let's prove it. Let's prove that L is dense in E. So for this we use a proposition that we actually, I mean, that we went through when we talk about the Hahn-Banach theorems and frames. So I strongly invite you to watch that video. I think it was the very first video of this lecture series. So go and check that out, please. So let F be an element of a linear bounded operator, and such that F restricted to L equals 0. So in view, I mean, in order to prove that L is dense in E, so in view of, I think it was corollary 1.8, I'll put the link. We only have to, I mean, you have to prove that f equals 0. When I put 0, I mean, you understand that it's actually the 0 of the of E star. Okay, good. So given epsilon positive, right, there exists, because remember the dual space is actually separable, so given epsilon positive there exists a rank n, right, such that this is actually in n, such that the norm of f minus fn strictly less than epsilon, right? This is just by separability, like fn, it's a dense, it's a countable dense subset of the dual space. So we have 1 over 2 of the norm of fn, capital N, right, is less or equal than we saw that it was actually less or equal than fn xn, right? So which is again equals to, this is actually equals to fn minus f, the dual pairing between fn minus f and xn, right? This is, this holds for the simple reason that f affected to, let me just put it, because f restricted to L is equal to 0, right? So this means fxn, right, because xn is actually in L, so this is 0. And now we know that this quantity here actually is actually strictly less than epsilon. So it follows that the norm of f, if you use triangle inequality, this is the norm of f minus fn, right, plus norm of fn, right, this is strictly less than epsilon plus 2 epsilon, right? So the whole thing is actually this is 3 epsilon. So I can make epsilon arbitrarily small. So we can conclude that this f equals to 0. So this is as epsilon was arbitrary. So as L is dense in E, minus L0 is countable, dense subset of E. So this means E is separable. And then we are done. Good. So now let's take some consequences of the above theorem. So corollary 3.27. So let E be a Banach space right, then you have the following equivalence. So let me put it in this color. So E, the space E is reflexive and separable, right, if and only if the dual space E star is reflexive and separable. Okay, good. Proof. Okay, I mean we have already one implication, right? So we already have from corollary 3.21 and theorem, the above theorem, that was theorem 3.26, but let me highlight. Corollary 3.21 was actually on when we talk about reflexive spaces. So we already have from that I mean, if the dual space is reflexive, right, then E is also reflexive. This was actually from corollary 3.21 and theorem 3.26. Just tells us that if E is separable, then if the dual space E star is separable, then E is separable. So E star reflexive and separable obviously implies E reflexive and separable. Okay, good. So now conversely, right? So this will be the other implication. So conversely, I think this proof is rather easy. So conversely, if E is reflexive, right? Remember, and separable. Let's say. Remember the definition of reflexivity. So this means the bidual is equals to the image of E through the canonical embedding that we call D. So thus, so is bidual. So thus E is actually E star is reflexive and separable. Right, because of this conclusion here. This conclusion here just comes from this implication, because in the in this step we prove that if the dual space is reflexive and separable, then E is actually reflexive and separable. So we have that here. Conversely, we have that we assume that E is reflexive and separable, right? So, but reflexivity means that the bidual is equal to the image of E, right, for the canonical embedding. So the bidual is actually also reflexive and separable, right? And then by the first implication, this means that E star is actually reflexive and separable. So there's, this was rather straightforward. So this ends the proof of this corollary. Okay. So separability properties are actually, are closely related to the metrisability of weak topologies. So, but let's recall, right? Let's recall that a topological space X is said to be, it's metrizable if there exists, a metric on X, right, that induces the topology of X. So, but let's take this theorem actually, right? It actually shows the link. So theorem 3.28. Okay, so let A be a separable. So let A be a separable Banach space. It looks ugly. Separable Banach space. Right, then let me highlight separability. It's very important. Then the closed unit ball. Then the closed unit ball in the Joule space is metrizable. Is metrizable in the weak star topology. Sigma is tie. And conversely, if the closed unit ball is metrizable right in the weak star topology, then the space is separable. In the weak star topology, sigma is star E, right? Then the space E is separable. Good. Of course, there is actually a Joule statement. I think before going into the proof, let's state the Joule statement. The Joule version, right? So theorem. We'll come back to the proof, so don't worry. Theorem 3.29. So let E be a Banach space again, but this time not separable. So let E be the Banach space such that the Joule space is separable. Then the closed unit ball in E is metrizable. Is metrizable in the weak topology. Sigma E is star. Conversely, if the closed unit ball is metrizable in the weak topology, right? Then the Joule space is separable. Okay, good. So proof first, proof of theorem 3.28. So start with the first implication. So let E be a separable Banach space. Be a separable Banach space, right? And let's prove that. Let me put it in color. Let's prove that the closed unit ball in E star is metrizable in the weak star topology. In the weak star topology, sigma E star E. Okay, good. So we definitely have to construct a metric, like a distance on the closed unit ball in E star. So let xn, right, say n vector equal than 1 be a dense countable subset, right, of the closed unit ball in E. E is actually separable, so such a sequence always exists. Okay, so for every linear bounded operator f, right, put it in column. So this is why we define our metric. So we call it norm of f, right? So this norm is actually square bracket for this norm, just to make the difference. So the norm of f is defined to be the summation over n moving from 1 to infinity of 1 over 2 to the power n of the absolute value of f comma xn, right? So I think you can easily check that this is a norm, right? It's clearly a norm on the dual space E star, right? And that this norm is actually less or equal than the operator norm. Okay, now let g of f g, right, be defined as the norm of f minus g, right? So be the metric. So this is actually the metric induced by the norm. Okay, good. Now what you have to do is that we shall prove that the topology let's call it tau, right, induced by the metric g, right, on the closed unit ball in E star, it's the same as the weak star topology restricted to the closed unit ball, the same as the topology sigma E star E restricted to be A star. So so to speak, you have to prove that the tau is equals to sigma E star E, but restricted to the closed unit ball in E star. Okay, so you have to prove that the two topologies are, that they coincide. Okay, so we know what to do, right, when it comes to proving that two topologies are the same. So the first thing, so we start with the first equation, right? So I have to show that all open set for the weak star topology, right, restricted to the closed unit ball, is actually an open set for the topology tau induced by the metric G on the closed unit ball. So let F0 be an element of the closed unit ball in E star, right? And let call it and let V, right, be a neighborhood of F0 for the weak star topology, sigma A star A. So you have to show that, let me write it right, I think it's better. So you have to show, that V is a neighborhood of F0 for the topology tau. So basically what you have to do is that you have to find, some R positive such that the set U defined to be the set of F in the closed unit ball in E star such that the distance that we defined above, F0 less than R, is contained into V. Okay, good. So we need to find R positive such that the set U is actually contained into V. Okay, so as usual, we may always assume that, we may assume that V has the following form, right? So V is actually the set of F in the closed unit ball such that the absolute value of a Joule pairing, right, of F minus F0 on, say, yi simply less than epsilon for every I moving from 1 up to k, right? This is of course for some epsilon positive and y1, y2 up to yk in A. Good. So now without loss of generality, we may assume that the norm of y, say yi, right, is also equal than 1 for every I moving from 1 up to k. Otherwise you can always kind of normalize it, right? So okay, so now since xn, right, is a dense subset of the closed unit ball in E, right? So for every I moving from 1 up to k, right? So there exists say ni, right, in n such that the norm of yi minus xni, but so remember what I said in the beginning, right? Being separable means that no matter where you are, you can always find, a friend close by, right, that you can visit. Yeah. So now choose R positive, right? Small enough that two 2 to the power ni times r strictly less than epsilon over 2 for every I moving from 1 up to k. Okay, so I mean, if you don't understand where this comes from, I mean, there's no problem. You can even forget about this statement here. So okay, so our first claim is that for such R, so claim for such R, right, U is actually contained into V. So indeed, this is what you are going to prove. Then you will see how this inequality emerges. So indeed, if the distance of F to F0 is less than R, right? So this means by definition of that distance, this means that the summation, right, over n going from 1 to infinity of 1 over 2 to the power n of the absolute value of, so this is f minus f0, comma xn, right, is actually strictly less than R. So we have, I mean, if you have the sum of positive terms that are actually less than R, that means every term is actually, I mean, it's less than R. So you have 2 to the power ni of the absolute value of f minus f0 at xni, right, the dual term, is actually strictly less than R, and this for every I moving from 1 up to k. So, and therefore, for every I moving from 1 up to k, right, the absolute value of f minus f0, like that yi is equal to, I mean, this is kind of triangle inequality, but let's go step by step. So this is f minus f0 at yi minus xni, right, plus the loop pairing between f minus f0 at xni, so the absolute value. So this is actually strictly less than, I mean, if you use triangle inequality here. So this is, and then you also use the fact that f and f0 are actually linear bounded operators. So this is also equal than the norm of f plus the norm of f0, operator norms of course, times the norm of y I minus xni, right, plus the absolute value of f minus f0 at xni. Oops, forgot to close the dual pairing bracket. Good. So, but now observe that this is actually also equal than 1, because I mean those are actually chosen to be in the closed unit ball in E star, right? And also this is actually slightly less than R times 2 to the power ni. Okay, so, and also we saw that, I mean, this is actually, oops, we saw that this is actually less or equal than epsilon over, I think it was epsilon over 4. Yeah. So if you use all those bounds, so you get this is slightly less than epsilon over 2, right, plus R I times 2 to the power ni. So now you see that, I mean, if you choose this in such a way that, I mean, this is actually slightly less than epsilon over 2, then you get that this is actually slightly less than epsilon over 2 plus epsilon over 2, but which is actually epsilon. So this means that the absolute value of f minus f0 at yi slightly less than epsilon for every I moving from 1 up to k. And this is exactly the definition of being f. So it follows that f is an element of V. Hence the weak star topology, right, restricted to the closed unit ball. B star is actually contained into the topology induced by the metric Z. Okay, so B is actually the order inclusion part, right? So now let F0, right, in B star, right? So given positive, so you have to find some neighborhood. You have to find some neighborhood, say V, right, of F0, but this time for the weak star topology, right, such that V is actually contained to U. So U is actually set of F in B star, such that the distance of F to F0 is equal to R. Okay, good. So we shall choose V to be we should choose V to be of the form, because we know how to characterize neighborhood of a point for the weak star topology. So V should be of the form F in B star, such that in absolute value F minus F0, comma xi strictly less than epsilon for every I moving from 1 up to k, right, with of course epsilon positive. So let me just with epsilon and k to be determined in such a way that V is contained to U. Okay, so for that we are going to do something not really crazy, but what we are going to do is that we will move from what we want to achieve, right, to find sufficient condition for what we want to achieve. It sounds like a tautology, but let's see what I mean. Okay, so for F in V, right? So V is constructed. So you have the distance of F to F0, right, is equal to, this is by definition the summation, and moving from N to, I will split the sum directly, right? So don't get confused. The value of F minus F0 xn plus the summation over N, now moving from k plus 1 to infinity of 1 over 2 to the power n F minus F0 xn. So now this is actually strictly less. Remember, F is actually in V, so this is actually strictly less than epsilon times the summation over 1 of the 2 to the power n, and moving from 1 to k, right? So this we all agree. Plus, now I will just use the fact that F is continuous, and that so this is just the by continuity plus the norm of this, the operator norm of this, times the summation over n moving from k plus 1 to infinity of 1 over 2 to the power n times the norm of xn. Now, put it in color. Now observe that this quantity here it's actually less or equal than 1, right? So this is less or equal than 2 because f and f0 are actually in the closed unit ball, right, in E star. And also the sequence xn, you should remember, was chosen in the closed unit ball in E. So this is actually slightly less than epsilon plus 2 times the summation of 1 over 2 to the power n moving from k plus 1 to infinity. So, but we can even compute the that summation. So this is actually slightly less than epsilon plus 1 over 2 to the power k minus 1. So, but we want this bounds actually to be strictly less than r. So thus, we want this. So we want this to be strictly less than r. So thus, it suffices to take epsilon to be say r over 2, right? And choose k large enough, that 1 over 2 to the power k minus 1 is strictly less than r over 2. So hence the topology induced by the metric Z is actually contained to the weak star topology restricted to the closed unit ball in E star. So hence both topologies coincide. And this is what we had to show. Okay, good. Okay, now let's try to prove the reverse implication. Right? So now reverse implication, because we saw that the converse is also true. So conversely, now suppose that that the closed unit ball in E star is metrizable, right, in the weak star topology, sigma E star E, right, and put it in color. Now let's prove that E is separable. Okay, so for that, put un to be define un to be the set of f of linear bounded operator with norm less or equal than 1, right, such that the distance of f to 0 of E star is actually strictly less than, let me just drag it to the left. It's actually strictly less than 1 over n, right? So n greater or equal than 1, of course. So, and that Vn might be a neighborhood of the origin, right? In the weak star topology, sigma E star E is such that say Vn is actually contained into Un. Okay, so again, we may assume that we may assume that Vn has the following form, so that the f in the closed unit wall again, right, such that absolute value of f, say x, right, strictly less than epsilon n, and this for every x in phi n, right, while phi n, I mean with, first of all, epsilon n positive and phi n being a finite set. Finite set of E. Good. Now put G, right, to be countable union of the phi n, right, n running from 1 to infinity, so that G is countable. Right, so now our claim is that the span of G is actually dense in E. So claim, we prove that. Claim is that the span of G, right? This means span of G is dense in E. So again, right, which implies that E is separable. So if you prove this, we are done. Okay, good. Indeed, so for the proof, we use our trick again that we saw in the very first chapter on the Rand-Banach theorem. So indeed, suppose you have a linear bounded operator, right, on E, such that f restricted to G equals to 0. So the goal is actually to show that f is vanishes identically. So it follows that. Of course, that f is actually into Vn, right, for every n, because f restricted to G is equal to 0, and 0 is actually less than epsilon n anyway. So f is actually in Vn for every n, and therefore f is in un, right, because we know that Vn is actually contained into un, so that f is, f vanishes identically, so f is actually 0. In fact, remember that just for your recall, f in un means that the distance of f to 0, right, 0, the 0 bounded linear operator, so characteristic less than 1 over n. So if you make so that n goes to 0, goes to infinity, then you have that this goes to 0 as n goes to plus infinity. So this means f is, you know the property of a metric, right? So this means f is 0. Good. So hence, from that we can conclude that the span of G, right, is dense in E. Is dense in E. So looks ugly. So hence E is separable. Okay, good. So this is what we have to show. So we are done. Okay, so let's comment a bit about the proof of theorem, of the Joule statement, right? So that is proof of theorem 3.29. Okay, so the proof of the implication is separable, right? Implies that the closed unit ball in E is metrizable in the weak topology. Sigma E star, right? It's exactly the same as the one in Chauvin 3.28. It's exactly the same as above, right? So just change the role of E and E star. However, the proof of the of the converse is a bit it's more delicate, right? So just write it. So however, the proof of the converse is it's more delicate. It's more delicate. But again, feel free to reach out to me if you face any difficulty, or if you would like to have a look at the proof. I'm here for you. So, okay, so remark, because I know some of you might be confused, so let's take this remark. One should emphasize, in finite dimensional spaces, the weak and the weak star topology, are not metrizable. So let me write it in, put it in color. In infinite dimensional spaces, right, the weak topology we put sigma E star, right, respectively weak star topology, sigma E star E, right, on all E, respectively all E star, right, is not metrizable. In particular, the topology induced by the topology induced by the norm we define above, right, on all E star does not coincide with the weak star topology. Does not coincide with the weak star topology. Only coincide on on the closed unit ball. Let me put it. It only coincides. When restricted to the closed unit ball. Okay, good. So corollary. This is corollary 3.13. 13, yeah. .13. Good. So let E be a separable Banach space. So let E be a separable Banach space, and let Fn, right, be, say, a bounded sequence of, a bounded sequence in E star, right? Then color, there exists a subsequence doesn't look nice. There exists a subsequence, say f and k, right, that converges in the weak star topology. The weak star topology sigma E star A. Okay, so proof. So if you have a separable Banach space, right, then you have a sequence of a bounded sequence of linear bounded operator, then there exists a subsequence that converges weak star. So proof, let Fn, right, so let Fn be in the bounded sequence in the Joule space, right, the bounded sequence in the Joule space, right. So without loss of generality, we may assume that the operator norms is the norm of Fn is less or equal than 1, right, for every n. Okay, so the set, we know that the set, the closed unit ball in the Joule space is actually compact, right? So this is actually by Banach-Alaoglu, Bourbaki theorem. So this is by Banach-Alaoglu. Bourbaki. You put the link to the video. So B star is compact and metrizable according to what we saw above. Metrizable for the weak star topology. Sigma E star star, right? So again, let me just say why. So because E is separable. Twice E is separable, so that is by I think it was theorem 3.28. So you have a compact, the conclusion just follows, right? So there's nothing to write anymore. So the conclusion follows, right? Because you know that when you're actually in a metric space, compactness means that any sequence has a convergent subsequence. So let me just write it. you have B star, right, with the metric G. So this is a metric space, right? Then another for a metric space, right? So B star compact means that any sequence has convergent subsequence. So this actually ends the proof of this corollary, and this is also the end of this lecture. So thank you very much for watching the video, and stay tuned, and we see each other in the next video.